Hey y'all, welcome back. Today we are reviewing for our Unit 7 test, which covers really just three major topics here. We're going to be doing a lot of u-substitution. That was the first thing we covered. And then we talked quite a bit. We had several days where we went over separable, if I can spell, separable differential equations. And then the last topic that we covered, which is really just kind of an offshoot of those separable differential equations, was slope fields. So these three topics are what we're going to focus on this review. You can expect that the test will cover the same content. I wouldn't expect the exact same problems to be on that test, but they should, if you feel comfortable with all the material on this review, you should have a high degree of confidence that you're going to perform well on the test. So let's get into the problems. Number one and number two, we're solving for y. It says solve each of the following and write your answers as y equals f of x. In other words, let's solve for y, isolate y in each of these problems. Now, both of these are going to be separable differentiable equations where separable differential equations where we have to separate out the y's from the x's. And once we do that, we can integrate and kind of go from there. So number one says dy dx equals 3 sine x over y. So to separate the variables, we need to multiply both sides by y and also multiply both sides by dx. Do a little cross multiplication there. And we get y dy equals 3 sine x dx. Now, once you separate the variables, you do want to integrate both sides. So we got the integral of the left side, integral of the right side. We don't have any composite functions here, so there's not going to be any u-substitution to worry about. The integral on the left-hand side, the integral of just y, is going to be 1/2 y squared. We're just using the anti-power rule there. And on the right-hand side, the integral of sine is negative cosine. So we get negative 3 cosine x, and then, of course, we've got the plus c. So from here, we are going to isolate y, and you shouldn't have too much trouble isolating y. But once you isolate y, you do need to go back and figure out what the c value is. So we'll come back to that. But to isolate y, I'm going to multiply both sides by 2, giving me negative 6 cosine x. And I do technically need to multiply that c by 2, but we've talked quite extensively about this, how you do not actually need to keep track of the manipulations that are happening to c on paper. 2 times a constant is just going to be a constant, and so we're just going to leave it like that. Now, when you go back and solve for c, if you solve for c here, got a little off. Oh, what's going on here? If you solve for c on this initial equation, you will get a different c than if you solve for c on the next equation. I mean, you can see that this c over here should be twice as big. So it doesn't really matter which one you use to solve for c, in the sense that you can still get the right answer either way, but whatever equation you use to solve for c, you're going to want to use that equation to go back and plug c in. So if we solve for c here, up here, then we're going to need to plug c back in here, and then when we go and actually isolate y, we'll multiply by 2, and it will end up to be the same c that we get here. So I just want to kind of make that clear that these two c's are not the same, and when we go back to solve for c, we need to be careful about where we're putting it. So finally here, we do need to take the square root of both sides. So y will equal, now when you take the square root of y squared, it does become absolute value of y, and that's where we get that plus minus business coming from. Anytime you want to undo an absolute value, you do have to decide plus or minus here. Y needs to be a function, so we have to decide on plus or minus. Now, since this point that was given has a positive output, we are going to choose the plus over the minus. So we're going to have positive square root of negative 6 cosine x plus c. So that's the general solution, but we do want the particular solution. In other words, what we just found are a family of functions, or is a family of functions whose slope is given right here, but we also needed to go through that point 0, 2, and that's how we're going to get the c, is we're going to plug in 0, 2. Now, the c value does get modified from here to here when you multiply both sides by 2. Okay, so, but it does not get modified when I go from here to here, because I'm taking the square root of the whole thing, and the c is still kind of stuck underneath that square root. So those c's are the same, So that first equation that I get where there's no more manipulations of c happening, that's the one that I'd like to use to solve for c. So plugging in 0, 2, I get 2 squared equals negative 6 times cosine of 0 plus c. Cosine of 0 is 1. So we have 4 equals negative 6 plus c. Adding 6 to both sides gives me 10. So my final answer here should be y equals the square root of negative 6 cosine x plus 10. Number 2 will be solved similarly, although actually, it should work out pretty nicely. We are going to have to do a little u-substitution, I think. No, maybe we won't need to. Let's just go ahead and start working it out. Actually, I don't think we're going to need to do a u-substitution here. So to solve this one, we are going to start off the same way we did number 1. We're going to separate those variables. So we're going to divide both sides by that square root of y. Now, dividing by square root of y is the same thing as raising it to the negative first power. Square root of y is just y to the 1/2. So when we raise that to the negative first power, we're going to get y to the negative 1/2. So I just want to make sure that algebra is clear to you, like where that negative 1/2 is going to come from. So we've got y to the negative 1/2 dy equals 3x squared plus 4 dx. Now I'm going to integrate both sides, and I can just use the anti-power rule on both sides here. So increasing that negative 1/2 by 1 brings that exponent to be 1/2, and I do need to divide both sides. I need to divide that by 1/2. And dividing this by 1/2 is equivalent to multiplying by 2. So we've got 2y to the 1/2, 2 times the square root of y, equals x cubed plus 4x, and then, of course, the plus c. Then I can divide both sides by 2, giving me the square root of y equals half x cubed plus 2x, and this c does get modified, right? C divided by 2 should become a different number, but it's still a constant, so I'm not going to keep track of that modification, but when I go to solve for c, I'm going to want to use this one rather than the previous one so that I don't have to worry about the c changing value. Now finally, to get the general solution, I'm going to square both sides. So I get y equals 1/2 x cubed plus 2x plus c, all that squared. And so the last thing I need to do here is actually find c. So to find c, I'm going to use that coordinate that was given, the 3, 9, and plug that into x and y. So y to the 1/2 is equivalent to square root of y, so square root of 9 equals 1/2 times 3 cubed plus 2 times 3 plus c. So the square root of 9 is 3, of course. 3 cubed is 27, so we have 27 divided by 2. Ugh, what is that? I guess that'd be 27 divided by 2. 28 divided by 2 would be 14, so 14.5. Does that check out? I think that's 14.5, so 14.5. Let me think about that one more time. 27 divided by 2, 28 would be, no, it should be 13.5, sorry. Yeah, because 13 times 2 would be 26, and then 2 halves would bring it up to 27. So yeah, so 27 divided by 2 is 13.5 plus 6 plus c. So here we've got 3 equals 19.5 plus c. And if I subtract 19.5 on both sides, I get my c value is negative 16.5. So that's my c, and now I'm ready to write my particular solution here. In other words, the equation that has the given slope and goes through the given point is 1/2 x cubed plus 2x minus 16.5, all that squared. All right, number 3 says find the equation of the curve that passes through the point negative 1, 0 and has this slope. That's your dy dx. So yeah, this is the same kind of question that we worked on in number 1 and number 2. We'll set up our differential equation here, dy dx equals 4x plus 5 over e to the y. We're going to separate our variables by doing a little cross multiplication here. E to the y dy equals 4x plus 5 dx. And then integrate both sides. The integral of the left-hand side is just going to be e to the y. Okay, that exponential function is its own integral, as is also is its own derivative. Equals let's see, x squared, 4 divided by 2 is 2, so 2x squared plus 5x, and then we have our plus c. Next, to isolate y, we're going to take the natural log of both sides, and so I get y equals the natural log of 2x squared plus 5x plus c. So that's my general solution. But now I'm going to figure out what c is, and I'm going to use this one. This is the last, or really the only step. I guess you could use either one, but if I try to plug in the point -1, 0 into the last equation, that general equation, my first step is going to be to exponentiate both sides anyway. So it's just going to take me back to this step. I'm going to save myself a step by just using the one I have notated here. So e to the 0 equals 2 times -1 squared plus 5 times -1 plus c. E to the 0 is 1, 2 times 1 is 2, 5 times -1 is -5. So 2 minus 5 is -3. Add that 3 to both sides, we get c equals 4. So my equation, my particular solution here will be y equals the natural log of 2x squared plus 5x, and then plus our c, which is 4. Number 4 says if dy dx is y times secant squared x, and y equals 8 when x equals 2. Okay, so this is just kind of another way of stating the initial condition, 0, 8. It needs to be on the point. So we'll solve this just like we've done all the previous problems. This is going to be another one of those separable differential equations that we can solve. So yeah, we're going to divide y on both sides. That's going to give me y to the -1 dy equals secant squared x dx. And actually, I'm going to give myself a little bit more space there because I do need to integrate both sides. So we got, let's rewrite that, secant squared x dx. Okay, so yeah, now I want to integrate both sides to try to solve for that y, because that's, this is a multiple choice question, but we do still need to go through the steps. So make sure you're showing all your work. Even though it is multiple choice, if you show your work, you'll be much less likely to make an error. So the integral of y to the -1 is going to be the natural log of the absolute value of y equals the integral of secant squared. We haven't seen this one in a while, but you still are going to be required to know what the derivative of tangent x is. And the derivative of tangent x is secant squared x. So the integral of secant squared x is tangent x. So we have tangent x plus c. Now to isolate y here, we're going to have to exponentiate both sides. So you have the absolute value of y equals e to the power of tangent x plus c. Now because we have this 0, 8, that our output for this one is going to be positive. So when we get rid of those absolute values, we're going to choose plus rather than the minus. So my general solution here is going to be y equals e to the tangent x plus c. Okay, I would have a plus or minus there. Got to pick one. We're going to pick the plus. Lastly, we need to find the c, and I think the easiest way to find c here is going to be with this equation. C does not get modified independently after that. So let's figure out what that is. We've got, let's see here, the natural log of 8, and it does say absolute value of 8, but the absolute value of 8 is just 8, equals tangent of 0. Now, tangent of 0 is just 0. It's the y value divided by the x value at 0 radians. So it's going to be 0 plus c. So that means c is the natural log of 8. Okay, so we've got y equals e to the tangent x plus natural log of 8. And that is our particular solution. However, after looking at these answer choices, you might notice that that's not any of the answer choices. So what's going on there? Well, what's happening is, and you're going to see this really anytime you have one of these kinds of questions as a multiple choice question, is whenever you've got like e to some power and that exponent is a sum, you can use the the product property of exponents. Like if you have e to the x times e to the y, we can combine these two terms by adding the exponents. But you can also take that property backwards, so that if you have a sum in the exponent, you can break it up as like e to the tangent x times e to the natural log of 8. So in other words, you could write this as e to the tangent x times e to the natural log of 8, and e to the natural log of 8 is just 8. So we have 8 times e to the tangent x, and we can see our answer then is B. Now, one thing you can do, because this is a multiple choice question, is sort of take advantage of its take advantage of the fact that it's multiple choice. Uh, you can go through, and let's say you sort of forgot how to work a problem like this. You could go through each of the answer choices, differentiate them, and see which one is actually y secant squared x. You want to be careful, because when you differentiate, it's all going to be in terms of x, but y would just be the original function. So like if I differentiate this one using the chain rule, I should get y, which would be like 8e tangent x times secant squared x. So yeah, just be looking out for that. You could kind of work this one backwards. It'd probably take a lot of time because you'd have to check all 4 answer choices. But if you got the time, you could definitely kind of work backwards there. Number 5 says using the substitution u equals root x, this integral is equal to which of the following? So this is going to be a u substitution problem, but they actually give us what the u is. It's x to the 1/2 power, or the square root of x. Now, if u is x to the 1/2 power, that means du, which is the derivative here. Don't get confused. We've been doing a lot of integrals here. So when you differentiate, that's what we did in the first semester. You might be tempted to just if you're just kind of going through the motions, you might integrate this on accident. But we do want to differentiate it, which means we want to bring that power down, and we want to subtract 1 from the exponent. So we get x to the -1. Now, just to be clear here, if, kind of taking a look back at this equation, so we're going to have to do a u substitution, and I did forget the dx on there. It might be worth rewriting this as 1 over 2 times root x. And so you can it's a little bit more obvious to see that we do have 1 over root x. We don't have 1/2 over root x. So we will need to multiply both sides by 2. So 2 du would then be 1 over root x dx, which is something that we have in there. So now we can rewrite this. I'm going to hold off on the bounds here because we do need to change the bounds. But we have this not the square root, the integral of e to the u. Okay, that's that numerator here, right? Times 1 over root x dx, and that is our 2 du. So times 2 du. Now, this is a multiple choice, and our multiple choices are all in terms of u. So we don't have to go back and resubstitute the x's, but what we do need to do is change the bounds. So the boundaries initially were 4 and 1. These are x values. These are partitions. Don't forget that when you're finding an integral, what you're really doing is finding the area under the curve. And when you're finding a definite integral, you're finding that area in between x equals 1 and x equals 4. But again, these are x values. So when we convert everything to u's, we also need to convert the bounds so that they are in terms of u. So luckily, we already have an equation for that conversion. It's the one that was given to us. U is the square root of x. So the square root of 4 is 2, and the square root of 1 is 1. So the bound should be from 1 to 2, and so our answer should be C. On number 6, it says shown is the, okay, I might want to clean up the grammar there, but shown is the slope, or maybe that does make sense. Shown is the slope field for which of the following differential equations? I don't know why, but reading that out loud, I feel like we could word that a little better. Basically, you're just trying to do a little match here. Which one of these differential equations would produce that slope field? So there's a couple of different strategies you want to try to work with on this. One is just to look for patterns. But another thing you could do is just plug in points. Plug in points where the slope is obvious. Here's an example. So notice how all the slopes along the x-axis are 0. And so basically what that's indicating is that when y is 0, I might have said x earlier, when y is 0, the slope equals 0. And the slope is the dy dx. So we can go through the answer choice and see, hey, if I plug in 0 for y, does that force the derivative to be 0? And that does for choice C, but it also works out for choice D. Now B, this doesn't have to necessarily be 0 because there's no y here. So y being 0 is not going to force this derivative to be 0, so our answer is not going to be B. And it's not going to be A either for the same kind of reasoning. If y is 0, x could be like 1, and if x is 1, then the slope should be 1. But we can see at 1, 0, the slope is still 0. So it can't be A either. So it's either going to be C or D. And so what we're going to look for is like, okay, so our choice is going to be either y squared or y cubed. So let's find a coordinate like where the slope is like obviously 1 here. And I think, if I choose 1, 1, actually it looks like no matter what y is, if y is 1, then the slope is 1. That's going to be true for both of them. That's not going to be particularly helpful. But what if we have a negative slope? Like, let's say we have like a slope at x equals negative 1. So at this point, when y equals negative 1. So when y is negative 1, the slope is always 1, or at least approximately 1. We don't know for sure, but we can see it's approximately 1. So when y is negative 1, the slope is at least approximately 1. So let's see what happens with both of these. If I plug in negative 1 into this, negative 1 cubed is negative 1, so it can't be C. If I plug in negative 1 here, negative 1 squared is 1, so our answer has to be D. Number 7, what is the antiderivative of tangent x? Now, you could try to memorize this one, but honestly, I don't think it's worth memorizing because it's kind of a weird integral. It's probably going to be easier to just work it out. And to do that, you have to know that tangent of x is equal to sine over cosine. And if we're trying to find the antiderivative of that, we're going to use integration. So we're going to integrate sine over cosine. And to do that, we're going to have to use a u-substitution. So if we let u be cosine x, then du would be negative sine x dx. And although I do have sine, I don't have negative sine. So dividing both sides by negative 1 gives me negative du is sine x dx. And that is something that I can substitute. So making that substitution, I'm going to have the integral of 1 over u. Okay, so 1 over u times negative du. So 1 over u, another way of saying that is u to the negative 1. And then now I can integrate like we have done many times. This is going to be one that you really should know. The integral of u to the negative 1 or anything to the negative 1 is going to be the natural log of the absolute value of that thing. So we have the opposite of the natural log of the absolute value of u plus c. Now, we are looking for the antiderivative of tangent x, or really this should be pluralized there because we're going to have infinitely many antiderivatives. But to do that, we're going to have to solve for c. So to solve for c, no, we don't have to solve for c. What am I talking about? We just need to go back and substitute in that cosine x. So this is going to equal negative natural log of the absolute value of cosine x plus c. Yeah, there's no initial conditions here. I don't know what I was talking about solving for c. We just have been doing that so much. I'm almost just like running on autopilot thinking I'm going to need a c, but take a step back, think, wait a minute, no, we're just trying to look for the antiderivatives. We don't need to find the c. We're not asking for a particular solution here. Okay, number 8 says the equation is a particular solution to which of the following differential equations. So here you can look at those answer choices, and some of them have y prime, some of them have y double prime. This is going to be one where we just basically test y prime, y double prime into the equation and see which one is true. So y is given. So let's write y prime here. Let's figure out what y prime is. Y prime is going to be the derivative of 2 times e to the 6x. Differentiating that is going to require the chain rule because we have a composite function with that. If it was just e to the x, we could just go, yeah, this is going to equal 2e to the x, but it's e to the 6x, so we are going to need to do a little chain rule here. So if 2 times e to the 6x times the derivative of 6x, which is 6, so that's going to be 12e to the 6x. The derivative of negative 5 is just 0, so that's why it's just going to be the 12e to the 6x. Next, we want to find y double prime, and we can work it out very similarly. we're going to have 12 times e to the 6x times the derivative of 6x, which again is 6. And 6 times 12, gosh, what is 6 times 12? Let me think. That's going to be 72. So that's going to be 72 e to the 6x. Okay, so let me highlight these just to make it a little bit easier to see. Y prime is 12 e to the 6x. Y double prime is 72 e to the 6x. And so we are just going to test these into the equations and see which one ends up being true. So for choice A, we've got y prime, which is 12 e to the 6x, minus 6 times y, so that's 6 times 2 e to the 6x minus 5, minus 30. We want to know, does that equal 0? So let's simplify and find out. We've got 12 e to the 6x minus 12 e to the 6x. So far, so good. Plus 30, just distributing this negative 6 here, minus 30, that does in fact equal 0. Okay, so it's looking like, and I'm just going to pencil this in here, it's looking like A is going to be our answer. But let's just double check the other ones just to be on the safe side. Okay, we don't, if we get 2 right answers, then we're going to need to go back and find our mistake. So let's try B. We're going to basically work this out the same way. We've got 2 times y prime. So 2 times 12 is going to be 24 e to the 6x minus 12 times y. So let's see, 12 times 2 would be 24. 24 e to the 6x minus 12 times, yes, 12 times negative 5, or negative 12 times negative 5 is going to be positive 60, and then we have a plus 5. Okay, so it looks like the 24 e to the x are going to cancel out, but 60 plus 5 does not equal 0, so it's not going to be B. Okay, so just to save a little bit of time here, this is going to be how you check each of the answer choices. And I'm going to just go ahead and verify this, not C and D, but you really should go through and check those. Okay. Actually, maybe what I'll do here is just write it out, kind of speed up the video a little bit so you can kind of see how it's not going to be 0, and just not really talk through it. Okay, let's move on to these other integrals, which we are going to be using some more u-substitutions on. Number 9, we have the integral of 5x to the 4th over x to the 5th plus 9. So we could let u be x to the 5th plus 9. And if that's the case, then du would be 5x to the 4th dx. And we have exactly that. We have a perfect match. We got that 5x to the 4th dx right here. So making this u substitution should not be too bad. So we've got the integral of 1 over u du. So I'll write that as u to the negative 1 du. And this is going to be a pretty common integral that you have. We've done a lot of these where we have u to the negative 1 or x to the negative 1. This is one that I really hope you've got memorized at this point. But this is going to be the natural log of the absolute value of u plus c. And since u was x to the 5th plus 9, we could go back and put that in. So the natural log of the absolute value of x to the 5th plus 9. Oh, that should be an absolute value. And then we've got, of course, plus c. For number 10, we've got cosine of 5x times e to the sine of 5x. And so we've got sine x and cosine x. Since cosine is the derivative of sine, I think we're probably going to want to use sine of 5x as our u. So we'll say let u be sine of 5x, and then therefore du would be cosine of 5x, and then using the chain rule, we have to multiply by the derivative of 5x. So that would just be 5. And so I'll have cosine of 5x times 5, or 5 times the cosine of 5x. Either way, we don't have that 5 that we need. We just simply have dx. Oh, just simply have dx right there. So we need to divide both sides by 5. And so we have 1/5 du is cosine of 5x. And now I'm ready to do my u-substitution. So I have the integral of right here. That right here is e to the u. Okay, so I'm going to start with that, e to the u. And then the rest of this, cosine of 5x. Oh, I forgot my dx on here. Apologies. So we have cosine of 5x dx, and that is equal to 1/5 du. So we're going to multiply by 1/5 du. And the integral of e to the u is just itself. So I have 1/5 times e to the u plus c. And now I can go back and substitute in the x, the expression in terms of x. Since u is sine of 5x, I'll end up with 1/5 times e to the power of sine of 5x plus c. For number 11, I'm going to let u be x squared minus 6. And if u is x squared minus 6, du would be 2x dx. But I do not have a 2x dx in the expression. I've got a 7x dx. So I've got to change that 2 to a 7. And I can do that by dividing both sides of this du equation by 2 and then multiplying both sides by 7. So if I divide both sides by 2, that gives me this. But then I can multiply both sides by 7, and now I've got something that I can replace 7x dx with. So now I can go back and rewrite this as the integral of 1 over root u. So that would be u to the negative 1/2 times 7/2 du. Here I could just use the anti-power rule to integrate this. The antiderivatives of u to the negative 1/2 are going to be u to the 1/2. Then, of course, divide by the reciprocal of 1/2. Dividing by 1/2 is the same thing as multiplying by the reciprocal. So we can just multiply by 2. We still have that 7/2 out to the front. And then we have a plus c here. 7/2 times 2 is just 7. So I get 7 times u to the 1/2 plus c. Now, my final answer should be in terms of x here. So I'm going to go back and replace that u with an x squared minus 6. And there you go. You could also write this, you don't really have to, but since this expression is raised to the 1/2 power, you could potentially write it like this, or if it was a multiple choice question, it might be written like this. So just, be ready to be comfortable with either one of those two representations. Number 12 says a student attempts to solve a differential equation. Let me bring it up here. A student attempts to solve the differential equation dy dx equals x y cubed with initial conditions y equals 2 and x equals 0. So the point here would be 0, 2. The steps of the student's solution are shown. In which of the following steps does the error first appear? Okay, so let's see if we can follow this. First things first is we want to separate the variables. So we would have to divide both sides by y cubed. And usually when I'm working this out, that means I'm going to write it as y to the negative 3. But they just left it as 1 over y cubed. And yeah, that seems okay. Okay. Next would be to actually integrate both sides. Now, on the right-hand side, the integral of x is x squared times 1/2. So that seems okay. And then the integral of 1 over y cubed. Now, I would have to use, let's see, if I have y to the negative 3, I'm going to integrate that. This is going to be a power rule situation. So this would be y to the negative 2nd divided by negative 2. And here we go. That's not right. Okay, natural log is only used for when you raise something to the negative 1st power. Otherwise, if it's any other power, you're going to use that anti-power rule. So yeah, our answer is B. And then the follow-up here is to actually solve it correctly. So I guess I should have probably just done that from the start. So let's solve it correctly. First thing I'm going to do is separate the variables and bring the y's to the left and the x's to the right. Although, like I was saying earlier, I am going to write it a little differently than how they wrote it. This first step was correct, but I'm going to write it like this. Y to the negative 3rd power dy equals x dx. And then we want to go ahead and integrate both sides. So from here on out, we can just sort of ignore what's happening with all this because none of that's going to be right. Yeah, so we're just going to kind of work this out like we normally would. So to integrate the left-hand side, like we did before, I erased it before I realized that we have to work this out as well. We're going to increase that power by 1, and that's going to make it -2. So we have y to the -2nd power, and then we need to divide by that new exponent. So we're going to divide by -2 or multiply by -1/2. And the integral of x is 1/2 x squared. So now that I've got that, I've integrated both sides. I need to solve for y. So I'm going to first multiply both sides by -2. So I've got y to the -2nd power equals -x squared plus c. Now, just to be clear here, this c is now different than this c. We have changed the value of c because really I should have multiplied it by -2. So where am I going with this? What I'm saying is don't use this equation to solve for c. It's not like you can't do that, but you want to be real careful because that c is not going to be the same c as we get in our final general solution. So we're probably going to want to use this equation to find that c. We'll come back to that. But yeah, just be careful when you're finding that c because we are changing the value of c as we multiply both sides by -2. So to make that exponent a +1 on the y rather than -2, we need to raise both sides to the power of -1/2 because -2 times -1/2 is +1. So we get our general solution, y equals -x squared plus c all to the power of -1/2. Now you could write that as like 1 over the square root of -x squared plus c. You could write it like that, but I just think you don't really have to. I think this way is a little bit better. So now we need to find c, and like I said, I'm going to use this equation to do it. Okay, before I raised both sides to the -1/2 power. So using the coordinate 0, 2, I'm going to plug in 0 into x and 2 into y. So I've got 2 to the -2nd power. Now 2 to the -2nd power is just equivalent to 1 over 2 squared, or 1/4. But I'll show that on the next step. Equals negative, and then the x here is just 0, so 0 squared plus c. So yeah, this 2 to the -2 is really like 1 over 2 squared, which is 1/4. So my c value is 1/4. And now I'm ready to write my final answer. The particular solution really should be y equals -x squared plus 1/4 to the -1/2 power. And an alternate way of writing this, because we have that -1/2 power, is you could write it as 1 over the square root of -x squared plus 1/4. You don't have to write it like that, but that would be acceptable as well. Number 14, we're looking for the general solutions. So we do not have a point that we need to make sure our function goes through. We are going to give our answer in terms of c because we don't have a point to actually solve for c. So we're just going to go through the steps that we would normally need to go through to integrate these. So yeah, let's go. So 14a, we've got dy over dx equals 3x plus 2 to the power of 10. Now, because we do not have an x here or a y, we don't really have to separate the variables, but you could. I mean, if it just makes you feel a little better, we can do dy equals 3x plus 2 to the 10th dx, but you really don't need to, but that's fine. So now we're going to integrate both sides. And so the integral of dy is just going to be y. And the integral of this one, well, I think we're going to want to use a u-substitution here because we don't want to be multiplying that out 10 times. So I'm going to let u be, what should it be, 3x plus 2. So du would be 3dx. But since I only have a dx, I don't have a 3dx, I'm going to divide both sides by 3 and get 1/3 du is dx. So let's work this integral using that u-substitution. I'll rewrite this as the integral of u to the 10th times 1/3 du. And then I can just use that classic power rule on this. So I get 1/3 times u to the 11th, and then times 1/11, because we got to divide by that new exponent, plus c. And yeah, we're pretty much done here. We just need to go through and multiply those two fractions together to get the new coefficient, and replace the u with 3x plus 2. So our final answer here should be y equals 1/33 times 3x plus 2 to the 11th power plus c. And part B will be solved similarly. We do want to separate our variables here. So I'm going to multiply both sides by y plus 3 to the power 2/3. And by the way, if you see this y prime, that just means dy dx. Okay, that's the same thing. So we can just treat it as the same. So we've got y plus 3 to the power of 2/3 dy equals e to the 5x dx. And we are going to have to do some u-substitution really on both sides here. So on the left-hand side, maybe I'll just separate this out because we're going to have to do two u-substitutions. On this side, my u is going to be y plus 3. And so my du would just be 1 dy. And there we do have a perfect match. That's kind of nice. And we'll make that substitution. Oh, you know what? Why are we doing u-substitution if we're not integrating? Forgot to write those integral symbols. We do want to integrate both sides. So yeah, so now we've got the integral of u to the 2/3 du. And this is something we can use the power rule on. So we're going to raise that exponent by 1, which is 3/3. So 3 plus 2 is 5, 5/3. And then divide by the that new exponent. So if I need to divide by 5/3, that's the same thing as multiplying by 3/5. Okay, and now I can go back and sort of back substitute to get my equation back in terms of x and y, or in this case, just in terms of y. Since u is y plus 3, we get 3/5 times y plus 3 to the power of 5/3. Okay. So this is going to equal, and then we'll do the same thing on the right-hand side. Well, not the same exact thing, but the same sort of process here, where we've got a u that is going to be 5x, and du then would be 5dx. Now, in this case, I do need to modify the du because I only have dx, I don't have 5dx. So 1/5 du is dx. This u and 1/5 du is what I'm going to use for the substitution here. So I've got the integral of e to the u times 1/5 du. And the integral of e to the u is just e to the u. So we get 1/5 e to the u plus c, which would be 1/5 times e to the 5x plus c. Okay, this is getting a little messy. Let's kind of move this up here. I'm going to just rewrite that equation without any modifications, and then we'll go ahead and solve for y. So 3/5 times y plus 3 to the 5/3 equals 1/5 times e to the 5x plus c. And we are just trying to get the general solution here, so we don't need to find c. So let's not worry about that. We're just going to try to isolate y. So the first thing I'm going to do is try to get rid of that 3/5. And so I'm going to both multiply both sides by 5, which will work out nicely with that 1/5. 5 times 1/5 is just 1. And then divide both sides by 3. So I'm going to have y plus 3 to the 5/3 power equals, okay, so 1/5 times 5 is 1. 1 divided by 3 is 1/3. So 1/3 e to the 5x plus c. Now, technically speaking, when I divide both sides by 3/5 like that, that is going to modify the value of c. We don't really care at this point because we're not going to need to find c, but it is worth pointing out that the value of c just changed on us. Next, we need to get rid of that power of 5/3. And anytime you've got a power you're trying to get rid of, you want to raise both sides to an exponent that, when multiplied by the exponent that is there, gives you 1. So the fraction that I can multiply 5/3 by to make that a 1 would be 3/5. So we're going to raise both sides to the 3/5 power. So we have y plus 3 equals 1/3 times e to the 5x plus c to the 3/5 power. And then the last thing to do would be to move that 3 over, and that's going to give us our final answer here, our general solution. Y equals 1/3 e to the 5x plus c to the power of 3/5, and then have a minus 3. Should have probably given you more room for that one. But hey, we were able to squeeze it in, so no big deal. If we needed to find the c, I might be a little more annoyed that we didn't have so much space. Okay, number 15 says if g prime equals f, where g of -8 equals a, and g of -4 equals b, and g of -2 equals c, and g of 11 equals d. Okay, so we've got a lot of variables here, or a lot of this a, b, c, d. We're most likely going to have to use all 4 of those. So let's see where this is going. Express the value of this integral in terms of the given variables. So what we have is x times f of 1/4 x squared minus 5. So what we're going to want to do is do a little u substitution here. We're going to let u be 1/4 x squared minus 5, so that du can be, let's see, 2 times a fourth would be 1/2 x dx. Now in this problem, I do have x dx, but I don't have half x dx. So I need to multiply both sides by 2 so that I have something that I can actually substitute in there. So 2 du will be x dx, and now I can make the substitutions. So I'm going to go and kind of move this over here, and we will have to change the upper and lower bounds because we are substituting all the x's for u's, and u is defined a little differently. So since u is 1/4 x squared minus 5, we're going to plug in both -2 and -8. This is not something I think I can do just all in my head. I'm going to actually write it out. So the new u value for the top, okay, so the upper bound, I'll call that ub, upper bound. Maybe I'll just put top. Be a little bit more casual here. Is going to be 1/4 times the original top, -2, squared minus 5. Now -2 squared is 4. 4 times a fourth is 1. 1 minus 5 is -4. So that's our new upper bound, -4. And then the u value for the bottom would be 1/4 times -8 squared minus 5. Now 8 squared is 64. 64 divided by 4 would be, gosh, what would that be? 64 divided by 4. Why am I drawing a blank here? Well, 64 divided by 2 would be 32. Divide that again, it would be 16. So yeah, so we got 16 minus 5, which is 11. So our new lower bound is 11. And now I can write this in terms of u. So we've got, what do we have? We've got f of u, so fu, always fun to write that, then times 2 du. So I'm going to have a 2 out here and then a du over here. Okay, so now this is where we're actually going to go back to something that we covered in the last unit, the fundamental theorem of calculus. It's saying that g prime is f of x. So what that means, since the derivative of g is f, that means the integral of f is g. Okay, in other words, like if I integrate f here, that's going to give me g. So integrating f, I'm going to use that fundamental theorem of calculus and integrate the f, which is just g, of course. So we've got 2 times the integral of f of u, which would be g of u. So g of u from 11 to -4. Yeah, so let's go ahead and evaluate each of these. So we've got 2 times g of -4 minus g of 11. And I suppose that's where all those ABCs are going to come in play here. Let's move all this up. No, it's not going to let me do that. That's okay. We'll just make this work. So 2 times g of negative 4, that is given right here. That's b. So we've got b minus g of 11, which is given up here as d. So we have b minus d. Okay. So I guess that's pretty much it. Yeah, I mean, I suppose we could distribute the 2 if we really, we're just feeling like we need to do some more work here, 2b minus 2d. But that's going to be your answer. You probably could just leave it in factored form or go ahead and multiply it out. Either way, it's all good. 2b minus 2d should be your answer. Number 16 says, consider the differential equation. On the axes provided, sketch a slope field for the differential equation. So this looks and kind of sounds a lot more difficult than it really is. All you need to do is go through each of the 12 points, and that means we're going to negative 1 comma 3 would be the top left point up here, and basically go through each of these points and calculate the slopes. Now, as you're going through these, it might feel like it's a little tedious, at least in the beginning, when you're calculating these. But as you go through, you're going to notice certain patterns are going to emerge, and then it can kind of make this go a little faster. And so I'm just going to make a note of every point that I need here. There's going to be a total of 12 of them. So you got 0, 2, 0, 1, 0, 0, and then on that last column, we've got 1, 3, all the way down to 0, 3. Oh, sorry, all the way down to 1, 0. Okay, so here's our 12 points. And all you have to do is just plug in the x and the y into the differential equation. This dy dx, that is the slope of the function. And so we're going to draw a little line with that, whatever slope we end up getting at each point. So when x is negative 1, and y is 3, I'll work that up here. So when x is negative 1 and y is 3, we're going to get negative 1 times 1, okay, divided by 3 is going to be negative 1/3. So in the top left corner, we've got a slope that's negative 1/3. Down 1 over 3 is going to look, it doesn't have to be perfect, but it's going to look something like this. Negative 1/3. Now, if I do negative 1 times 2, the x is the same, but I'm changing the y. So this y now becomes a 2. 2 minus 2 is 0, so that's going to be 0. Now, anytime you notice you're getting a 0 slope, I think it's worth kind of thinking about what forced that to be 0. And it was the fact that y was 2. And so that means that this slope is going to be 0 anytime the y value is 2. Because if I plug in 2 for y, I'm going to get 2 minus 2 is 0, regardless of what x is. So for every point that has a y value of 2, I'm just going to go ahead and fill in those slopes as 0. And that's what I mean by just trying to look for patterns as you go. It can take a little while to do if you're really just doing this point by point. But if you notice something like, a 0 slope or an undefined slope, you want to be thinking about, what caused that to happen, and do any of the other points have that same characteristic? Kind of thinking along those same lines, another way that we can make this slope 0 is if we made x 0, because 0 times anything is 0. So if x is 0, then we're going to have a horizontal slope, and that means that every point along that y-axis, 0, 0, 0, 1, 0, 2, 0, 3, all those slopes are going to be 0. Okay, so let's move on to negative 1, 1. If I plug in negative 1, 1 to x and to y, so negative 1, 1, I'm going to get negative 1 times negative 1 is positive 1, so I get 1/3. And so that's going to look something like this. Now, if I plug in negative 1, 0, then I'm going to have negative 1 times negative 2 is going to be positive 2/3. So up 2 over 3 means this should be just slightly more sloped. It's not quite a slope of 1, so it shouldn't have that 45-degree angle, but it should be a little bit more sloped than we have above it. Now, you don't need to break out like a protractor or anything. You don't need to make this perfect. You're just trying to get kind of the general idea down. So at 1 comma 3, if I plug in 1 for x and 3 for y, I'm going to get 1 times 1 is 1 divided by 3 is 1/3. So get another 1/3 here. Really it's looking like we're going to have some symmetry here across that y-axis. So we probably have an even function here. So at 1 comma 1, we've got 1 times negative 1 over 3. So that'd be negative 1/3. And then finally at 1 comma 0, we're going to get 1 times negative 2 is negative 2. We're going to get negative 2/3. And so our slope field looks basically like that. When you're working these out, like on the test I'm going to give you, and even if this was a free response item, you don't really have to show all this work. I think it's helpful at least trying to get started. But once you start noticing the patterns, hopefully you can do some of these computations just mentally. It doesn't hurt to write it all out, but it does take time, and the AP test is timed. So that's something worth considering with these slope field problems. Now, on the AP test, I don't believe you're going to have to actually draw one out. It'll probably be more likely like a like a multiple choice question where you're trying to do some matching. So I wouldn't stress too much about it, but I'm going to give you one like this on the test where you do have to actually draw out the slope field. On my test, not the AP test, on this Unit 7 test. Number 17 says determine the solution to the differential equation with the initial condition that f of 3 equals negative 2. So a couple problems back over here when we were doing number 14, for those problems we're finding the general solution, meaning we didn't have to find c. But when you're looking for the particular solution with the given initial condition, that means we are going to have to find c. Now f prime is the same thing as dy dx. So I'm just going to rewrite this differential equation as dy dx equals x squared over f of x, which is y. Okay, maybe I'll make a little note here. This is dy dx over here on the left, and f of x is just y. So when I go to separate the variables, I'm going to have y dy equals x squared dx. I do need to integrate both sides to get rid of the dx and the dy. The integral of y is 1/2 y squared. The integral of x squared will be 1/3 x cubed, and then we need our plus c. So from here, we're going to try to isolate y, and then pick an equation to solve for c, plug that in, and then that's good. Then we'll be done. So if I multiply everything by 2, I'm going to get y squared equals 2/3 x cubed plus, it should be 2c, but since that's just a constant, we're just going to leave it as c. Now, because that value of c changed, I really don't want to use this one to find c. I want to use like kind of the last or the first time you've got a c value that no longer changes. Now, if I do want to isolate y here, the last thing to do would be to take the square root of both sides. So I get y equals plus minus the square root of 2/3 x cubed plus c. I do need to make a conscious choice on whether or not to keep the plus or the minus because y must be a function, so it can't have multiple outputs for any one input. And if I look at this one output that is given when x is 3, y is negative 2, that means that at least that point, we do have a negative output. And because of how this function's set up, where the plus minus is on the outside of that square root, that means that all the outputs are going to be positive or all the outputs are going to be negative. So since we know that at least one of the points has a negative output, that means they all need to have a negative output. So we're going to choose the minus over here. Okay, so that's our general solution, but now we're going to find the particular solution, and that means we need to find c. So to find c, you're going to use the given point, in this case 3, negative 2, to plug into x into y, and then solve for c. Now, I'll probably use this equation to solve for c because my c value did change from here to here, so I'm not really interested in doing it before that change. But the value of c didn't change from here to the next step. In other words, this c is the same as that c, because when I took the square root of both sides, I'm taking the square root of the entire function, and so the c value itself did not get manipulated. Okay, so we need to find c. So we're going to plug in 3, negative 2. So I've got negative 2 equals negative square root of 2/3 times 3 cubed plus c. Oh, you know what? What am I doing? I'm using the last question. Let's try that again. You could have done it that way, but that's just going to require an extra algebraic step. And I'm trying to stay consistent here. We want to use this equation. It'd probably be a little easier to find it anyway. So negative 2 squared equals 2/3 times 3 cubed plus c. Negative 2 squared is 4. And then 3 cubed is 27. So we got 2/3 of 27 plus c. 27 divided by 3 is 9, and 9 times 2 is 18. So I get 4 equals 18 plus c. And if I subtract 18 on both sides, I'm going to get c is negative 14. So now I've got all the pieces that I need to write my final answer, my particular solution that has the given slope and the given point. Negative square root of 2/3 x cubed minus 14. And that square root does need to extend over that c value. Okay, we've just got one last question, number 18. It says the rate of change of the population of a herd of deer is given by this differential equation where t is measured in years. When t equals 0, the population is 100. So we've got this initial point, 0, 200. Part A says write an equation of a line tangent to the graph at t equals 0. Use the tangent line to approximate the population of the herd after 2 years. So we're going to need a point and we're going to need a slope. And we're going to write our equation in point slope form, which is y minus y1 equals m times x minus x1. Since the point that's given is 0, 200, that's what I'm going to use for the point. I will have to calculate the slope though. Okay, I'm going to plug in 0, 200 into my slope formula to find that dp dt. So that would be 1 over 4 times 1200 minus the population when it's 200. So the slope, let's see, 1200 minus 200 is going to be 1,000. And 1,000 divided by 4 is 250. So my slope's going to be 250. So now I can write my equation. Y minus 200 equals 250, or not y. We're going to use, I guess we could use y, but since we actually have a variable here, let's do p. P minus 200 equals 250 times, and instead of x, I'm going to use t, because that's going to be what population's in terms of, t minus 0. Or you could just simplify this as p minus 200 equals 250t. So if I want to estimate the population of the herd after 2 years, I'm simply going to plug in 2 into the time and solve for p. So I've got p minus 200 equals 250 times 2. 250 times 2 is 500. So I've got p minus 200 equals 500. And if I add 200 to both sides, 500 plus 200 is 700. So this is my approximation. The way I want to say this is that the population in terms of time, or not in terms of any time, but at 2 years, so P of 2, should be approximately equal to 700. Part B says, using separation of variables, find the particular solution with the initial condition, the same initial condition, 0, 200. So let's separate the variables out, meaning we want the t's to the left and we want the p's to the right. So I'm going to divide both sides by 1200 minus p. And so I'll have 1200 minus p, since I divided both of those on both sides, I'm going to have to the negative 1 dp equals 1/4 dt. So now I'm going to integrate both sides. on that left side, I am going to have to do a u-substitution because I have a composite function. So I'll let u be 1200 minus p, which means du is just going to be negative 1 dx, or in this case, dt, or dp, sorry. So negative dp. So if it's negative dp, I don't have actually a negative dp, I just have the positive one. So I'm going to divide both sides by negative 1 and get negative du is dp. So anywhere I see dp, I can just replace that with a negative du and go on about my business, integrating the rest of the problem. So this will, on the left-hand side, will be the integral of u to the negative 1 times negative 1 du. Now, the integral of u to the negative 1, this is something we've done before many times, is the natural log of the absolute value of u. So I've got negative the natural log of the absolute value of u, and then of course there'd be a plus c, but I'm going to hang on to that. And then when I go back to substitute back in the u, it's 1200 minus p. I'll have negative natural log of 1200 minus p, close those absolute value bars, equals the integral of 1/4 dt, which is just 1/4 t. Okay, looking good, looking good. Let's keep it going. So what are we doing here? We are okay. So we need to substitute in 0, 200. To find c, but we still need to solve for p. Okay, we're not really done. We do want to get an equation for p here. So to do that, I'm going to multiply both sides by negative 1. So that'd be negative 1/4 t plus c. And then I'm going to exponentiate both sides, so I get the absolute value of 1200 minus p equals, let's see here, e to the negative 1/4 t plus c. Now on the left-hand side, I can go ahead and drop those absolute value bars. The population is going to be positive here. So I know this is going to be positive. So I've got 1200 minus p equals, and I'm going to rewrite this right-hand side. Okay, when I have e to the a plus b, that's equivalent to e to the a times e to the b. So in this case, if this is my a and this is my b, I can split that up and rewrite this as e to the negative 1/4 t times e to the c. Now this e to the c is just going to be a constant, so I'm going to actually call it c again, but I'm going to write it like this: 1200 minus p equals c, which is a different c than we had before, so it did get modified, so I don't really want to do any other c's except for starting from here. C to the power c times e to the power of negative 1/4 t. Now there's two more steps here to get p by itself. I do need to subtract 1200 from both sides. So let's erase this. Continue this up here. So if I subtract 1200 from both sides, I'm going to get negative p equals, well, maybe I'll put that minus 200 in the front because I just want to make sure that it's really just an aesthetic choice versus like saying minus 1200 on the back. The reason why I'm doing it this way is because this problem's getting kind of crowded, like just the physical space that we're writing in. And I don't want it to look like that minus 1200 is in the exponent. So I just think it'll just be a little bit more clear as we're working if we leave it there. So get plus c times e to the negative 1/4 t. And then I'm going to divide both sides by negative 1 to get my equation for p, which is 1200 plus c times e to the negative 1/4 t. Now I do need to get c. That's my general solution, not my particular solution. So I'm going to use the given point, this 0, 200, to figure out what c is. So if I put 200 in for p, Just going to switch colors here to make this easier, a little easier to read. So yeah, when the population is 200, that happens when time is 0. Okay, so if I subtract 1,200 on both sides, I'm going to get negative 1,200. Sorry, negative 1,000 equals C. And then here I've got 0 times negative 1/4 is 0, and e to the 0 power is 1. So it's just C. So C is negative 1,000. And so now I can write my final equation. P equals 1,200 plus, or no, it's going to be minus because C is negative, minus 1,000 times e to the negative 1/4 t. Okay, so that is my particular solution, but then it says use the solution to approximate the population of the herd after 2 years. Y'all, this is not going to be a calculator test, so this is not something I'm going to ask you to do. But if you were, on a calculator test asked to find P of 2, so the population after 2 years, you just throw in 2 into T and put this whole thing in your calculator and just calculate it from there. That's about as close as we can get without a calculator. I'm sure we could simplify a little bit, but there's really no need to. So let's just focus on what the actual equation is, which is 1,200 minus 1,000 times e to the negative 1/4 times t. And that's it for tonight's review. This was a little bit of a long one, but hopefully after going through some of these problems, you're feeling a little bit better about your understanding of u-substitution, of separable differential equations, and of slope fields. Again, those are going to be the 3 major topics that we cover on this test, and we're almost there. We only have one more full unit left before we take the AP test, and in that next unit, we're going to talk a lot about geometry, area, volume. It's a lot of good stuff. I'm looking forward to it. I hope you are too. Thanks for watching. Y'all have a great night.
Okie dokie.